Welcome to the Engineering Influence podcast, sponsored by the ACEC Life Health Trust. Today we are talking with Dirk Kestner, who is Director of Sustainable Design and a Principal at Walter P. Moore. The firm recently released a comprehensive report titled Embedded Carbon, a Clear Review of Carbon Emissions. Embedded carbon emissions occur before a building opens, as opposed to operational emissions that happen over a building's lifespan. They include carbon emissions associated with extracting, processing, shipping, installing, and maintaining the materials used in the building. The UN Environment Global Status Report predicts that during the next 40 years, we will build 2.5 trillion square feet of new building stock, which is equivalent to replicating New York City every month for 40 years. To reach the greenhouse gas targets set by the Intergovernmental Panel on Climate Change, we must significantly reduce the embodied carbon of buildings constructed during the next 10 years and reach net zero embodied and operational carbon soon after. The report outlines how complex getting to net zero carbon will be, requiring a multi-pronged approach, a combination of design optimization enabling dematerialization, decarbonization of the electrical grid, material impact optimization, and the inclusion of carbon sequestering structural solutions. So let's dive into it. In your report, you write, we must transition our design thinking from a linear approach, where the end goal is the building, to a circular approach where buildings are thought of as material banks for the future. The simplest way to reduce embodied carbon is to use less, either at the building scale or the material scale. You add, though, that current design practice is to optimize based largely, if not exclusively, on the cost and time of construction. How do we change this mindset?
Well, thank you. Time and cost in terms of dollars will always matter and be very important. But what we're increasingly aware of is that there are these externalities that we need to capture and roll into this. And we've seen some of that in the use of third-party rating systems such as LEED or Envision or Living Building, where these elements that aren't classically captured, the environmental impacts that occur, are baked into the point structure or the part of the rating system, or even in the case of the Living Building rating system where you actually do quantify your embodied carbon and then have to offset it through a series of pre-vetted offsets and pay a dollar amount to offset it. But we're also seeing some companies that are internally carrying a price for embodied carbon that are asking for a team to look at the operational and embodied carbon. And then as they make their decision-making process, they're weighing that. And there are a few jurisdictions, and I think increasingly we'll see more, that will carry a cost as well. Some of this mindset shift also relates to how we make some of these decisions that we've historically done, where we do think about economy in one way. Something as simple as concrete and formwork, where the labor cost of making different forms may have added more dollar cost historically, but now we could price the difference in terms of carbon of that added material and see how that changes the equation.
You addressed the incredible complexity of identifying and quantifying embedded carbon in the building process. You write, we are tackling a diabolical problem in a compressed time frame. As with many engineering tasks, quantifying embodied carbon involves working with uncertain data. And in the case of embodied carbon, uncertainty in these measurements stems from a variety of sources, material volume assumptions using industry averages, and different methodologies for developing impact factors, to name a few. How accurate can you be today? How accurate do you need to be? And looking forward, how accurate do you expect to be?
Right now, it's very hard to say that an estimate of embodied carbon in terms of, say, kilograms of CO2e is within, a certain percentage of, quote, true embodied carbon. However, there's two things that are very important that we can do and where the imperfect assessments are very helpful right now. They can be directional, and they will show us where the hot spots are in our structures or buildings or our infrastructure. So with these current assessments, and we can use comparative analysis and run different data sets through to bound it and come up with ranges, we're able to know enough to be able to take action and to ask questions about how we could optimize. Now, in the future, we'll have to be far more accurate, and we can prime the pump for that today by working with the ISO standards for lifecycle assessment and the product category rules, the environmental product declarations, making sure that suppliers know that we will be asking for this and that we're working to enhance the framework for data consistency and transparency so that we will be able to make better comparisons in the future.
On that point there, what role does the engineer in a design team working with an owner have in setting standards for suppliers?
I guess it depends on how the engineer views their role in some level. That the engineer as a specifier, every engineer will not, but that because we understand the importance of making these comparisons, we need to be part of shaping that ecosystem, if you will, of data collection and how to act on the data. I mean, I could see that being debated among an engineer saying, well, what's in my scope or what's not.
You highlight the strategy of dealing with the biggest embedded emitters first, and the biggest is concrete. You write that manufacturing concrete is an extremely carbon-intensive process that accounts for 4.4 billion tons of carbon dioxide annually, or 8% of the world's total global carbon emissions each year, making it the world's second largest CO2 emitter. The first step to reducing the carbon impact of concrete that should be done in every project every time is to optimize Portland cement usage. Another big opportunity, though, is reducing the amount of cement in concrete. You highlight some current cement alternatives, such as fly ash. But looking into the future, what advances do you expect in this area?
The area where we see the most advancement is in that binder, the glue that holds the rock together in concrete. And we're seeing some very interesting, right now at the university and academic level, research related to organic processes and that can lead to compounds that can hold the rock together and perhaps even sequester CO2 in the process. But while we see that in the long term and in the future, there's a number of steps that should be taken today as far as concrete, as far as optimization, that we don't need to wait for. And some of this relates back to some really basic steps, such as making sure that we are using performance specifications appropriately, being it minimizing the use of prescriptive specifications, having environmental performance specifications for concrete, as well as making sure that we're having deep dialogues with all members of the construction team, including the ready mix supplier, about what is driving the cement content of the concrete today, whether it's a requirement that's put on by the specifying engineer, one related to achieving construction or pumping or something like that, or something related to the local aggregate that's available. And there's also a lot of innovation going on within the manufacture of cement, such as Portland limestone cements or other cements that are still cement but are less carbon intensive.
Steel is another primary construction material, and it has a different problem because much of the carbon emissions are due to its high reliance on electricity to transform the raw material into its structural form. You say that we can expect some relief due to the projected increase in renewable resources in our electrical generation from 18% in 2018 to 31% of generation by 2050. Are there other near-term ways to reduce the impact of the electrical grid on embedded carbon in our buildings?
Well, yes. There's a great opportunity for materials that consume a lot of electricity in their manufacture, and that is that we know how to make renewable energy, and it can be a matter of incentivizing and understanding how suppliers who have these electrical intensive materials can drive the market to supply more renewable energy. So one of the best ways that a specifier could do that is to ask for embodied carbon information in the form of an EPD from suppliers of these materials. If then it's the case that a large portion of their impact is tied to the electricity that goes into their product, that gives them a very straightforward, not necessarily easy, but way to reduce the embodied carbon of that material. So as specifiers, we don't have to wait for the grid to decarbonize over time, but we can play a part in creating an incentive for that.
You do dedicate quite a bit of space in the report to reuse. Obviously, reusing a building rather than building a new one will substantially reduce the embodied carbon, as well as offer opportunities to improve the operational carbon performance of that building. But you also point to reusing materials that have already been made. For example, you report that construction and demolition waste represents approximately 40% of everything thrown away in the US each year, and that most of that material could have been recycled or reused. But that many regions don't have the infrastructure, and I might add the incentive, to effectively reuse. How do we get there?
Some of this comes back to where we started our conversation with the externalities and making sure we carry the cost of that material that would go into the landfill and is not reused, to show teams and show owners that there can be latent value in those materials. In some ways, as we start to design buildings for deconstruction, and we think about an existing building, not just as a building, but as a material bank or something where there is a carried value, that will help. And we can help, as we document buildings, to show how they are able to be deconstructed and to let the owner understand that there's value there. But the other part is making sure that we have an infrastructure and a supply chain to make those connections for that material that right now goes into the landfill, to show that once you're able to understand what's there, understand where it might go, that there's a pathway and that someone who's looking for this material can use it. So that creates value in that material. But sometimes it's as simple as having a warehouse or having a space for that material to sit, just because it can take time from when it comes out of the building to when it would go into the next one. A great example of that that's highlighted in the report is our involvement in the Life Cycle Building Center in Atlanta, a nonprofit, but where a group of designers came together based on occurrences and shortcomings of future projects and identifying that need in past projects to be able to have a space and make those connections for material that was coming out of one building and could go into the next.
Materials that could store carbon dioxide will be a key to offsetting the emissions from the other materials in buildings. Timber is the most obvious structural material that can sequester carbon dioxide, although you make the essential point in the report that we must consider not only the carbon sequestration of the wood, but also the impacts that come from harvesting, milling, and shipping this product. Given the importance of carbon sequestrating materials for achieving net zero, do we start using more wood in construction? And are there other sequestering materials available now or that you expect to come available in the future?
So I do believe that with the advent of technologies like cross-laminated timber, we will continue to see timber construction in ways and locations that we historically had not. But it's also very important to remember, as you correctly mentioned, that even for timber construction, there's a number of steps along the supply chain where we are emitting CO2. So that the act of measuring the total CO2 for the project and then looking at what's causing the CO2 emissions even in that timber building and how we can make those reductions is very, very important. When we look at some of the mass timber buildings that we're currently designing, every floor has 2.5 to 3 inches of concrete on it. So it's important as we are using the timber to store CO2 that we're thinking about the emissions from those other materials. There's some very interesting research going on other living and sequestering materials at the Living Materials Laboratory at CU Boulder with Will Schrubar. They're looking not only at things like cellulose-based composites, but biopolymers and biogenic cements, so that we could have sequestration not only in timber, but in those other materials that we use in construction.
Finally, at the beginning of your report, you referenced the World Green Building Council's report, which is called Bringing Embodied Carbon Up Front, in which, and I'm quoting here, they embraced a bold vision that by 2050, new buildings, infrastructure, and renovations will have net zero embodied carbon, and all buildings, including existing buildings, must be net zero operational carbon. How optimistic are you about achieving that?
I'm optimistic. It's a bold vision, and it may seem quite aggressive right now, but I'm also always amazed at what we can accomplish when we get a bunch of smart engineers together working on an identified problem. It really has only been the past couple years, perhaps 2 years, that we've seen broad awareness of embodied carbon in the AEC space. And we're seeing a number of different technologies that are emerging to address this. And we're also seeing teams go back and, by studying and measuring embodied carbon and having this as a metric that we're looking at, challenge past assumptions. So I'm optimistic, and I think it will be a combination of both rethinking some very classic things we do, as well as some new technologies that will be developed.
Great. That's a happy way to end. Thanks so much for taking the time to talk with us today.
Thank you for the opportunity.